Okay, the last lecture in our event today is by Stefano Profumo, The Burden of Proof.
All right, so thank you very much for the kind invitation, and thanks for having me. And I know it's been very hard to make it all the way to the very end of the conference in such a gloomy location, but you made it. Congratulations. So the picture we have of galaxies, such as our own Milky Way, is one where the luminous matter, stuff that we can observe and measure, is embedded in a halo of dark matter. There's very convincing evidence, as we've heard through this conference, that in fact, 4 out of 5 grams of matter in the universe overall, as a whole, are made of this dark matter. And there's also very compelling evidence that the dark matter itself is a new elementary particle. So there's no candidate within the particles we know and love that could be the dark matter. Now, to learn something about this new elementary particle, we need to detect it. And what we know, however, is that the dark matter is matter, so it interacts gravitationally, but there's no guarantee that there exists any other form of interaction between the dark matter sector and the ordinary matter sector. There exist, however, models where such interactions do exist, be them weak interactions of the kind that we know our particles experience, or dark force type interactions. In many cases, it makes sense to write down an effective type interaction between dark matter and ordinary matter. Here in the pictorial representation, particle physicists like me I have represented the interaction as an unknown blob. And in this case, the interaction is between 2 dark matter particles and 2 standard model fermions. And I don't really care about what exactly this interaction is. I just postulate that it exists and it couples to some combination of gamma matrices left and right, for example. So in many models, this is the type of process that sets the density of dark matter through, for example, thermal decoupling. And of course, if thermal decoupling did happen in the early universe, dark matter particles pair annihilate, and they pair annihilate today as well. If this type of interaction exists, there's also predictions for the direct detection of dark matter, which is the scattering of dark matter particles off of ordinary matter. And of course, you might hope to produce dark matter at colliders because, again, there is a channel that allows you to pair produce dark matter particles. There's also another possibility that is of interest, which is that the dark matter isn't in fact a stable species, but it decays. Now, of course, you got to postulate that the lifetime of the dark matter, since we do observe dark matter today, is much longer than the age of the universe, but this is a distinct possibility, that the dark matter is long-lived but metastable. Now, what I study is the debris, the possible debris of dark matter annihilation or decay. This is known as indirect dark matter detection as opposed to the direct detection of measuring scattering of dark matter off of ordinary matter. And the question that I like to address in my studies is, as a particle physicist, is whether or not we can do particle physics with indirect detection. Can we say something about fundamental interactions and constituents from studying the debris of annihilation or decay? Can we do fundamental physics with astroparticle or astronomical data? And if you look at the past, at the history of physics, this has been distinctly possible. So for example, dark antimatter was discovered in the cosmic radiation back in 1932. The fact that standard model fermions come in families and generations that duplicate themselves at different mass scales also was discovered in the cosmic radiation shortly thereafter. And the first hints of strong interactions in the discovery of pions was also obtained through observations of cosmic radiation. And much more recently, the fact that neutrinos don't look like the way they should if we knew everything about the standard model was discovered also in cosmic ray experiments. So today, What I'm going to do is I'm going to tell you guys about 3 tantalizing signals in indirect detection that might have something to do with a new breakthrough, a new discovery, that of the fundamental nature of dark matter. Here they are. A growing positron fraction as a function of energy, a 3.5 keV line, so this is an X-ray excess, a 3.5 keV of energy, and finally, an excess of gamma radiation from the center of the galaxy. So notice, incidentally, that the dark matter candidates that have been advocated to explain these excesses are at completely disparate energy scales, in fact, differing by more than 6 orders of magnitude, which exemplifies how little we know about what the dark matter can possibly be. And my attitude today will be one that will try to follow Carl Sagan's famous quote that extraordinary claims require extraordinary evidence, and the burden of proof is on such claims. So let me get it started with the cosmic ray positron excess. The fact that by looking at the fraction of positrons to the sum of positrons plus electrons in a cosmic radiation could be used to search for dark matter has been known for several decades, in fact more than 25 years. And in particular, the cool thing about this measurement is that if you have a rising positron fraction and a cutoff, you might even know and derive something about the particle dark matter mass. So it's very exciting. And it became more and more exciting as early cosmic ray balloon-borne experiments in the 90s showed first evidences that, in fact, the cosmic ray positron fraction rises in the few GeV energy range. This was confirmed with a tantalizing amount of data by the Pamela satellite experiments in 2009. It was confirmed with Fermi observations, and notice that this was highly non-trivial because Fermi does not distinguish directly positrons and electrons. It was a very clever measurement that I had the good fortune to be part of. And finally, and more recently, the alpha magnetospectrometer on board the International Space Station has confirmed with beautiful statistical accuracy that yes, the positron fraction increases with energy in the 10 to 100 and beyond GeV range. So why is this a big deal? It is a big deal because we are firmly convinced that in any cosmic ray model that works, that is predictive, positrons are secondary particles. And if that's the case, for sure, the positron fraction should decrease. It's very simple physics that explains this. And the simple physics is that the Larmor radius that we know of and we study since kindergarten, depends linearly with rigidity or with the energy or momentum of the particles. And this means that the diffusion coefficient is a positive power of the energy in galactic cosmic rays. So if that's the case, necessarily secondary particles decrease because they're produced by particles that have diffused and they've lost energy. And therefore, you always have a decreasing positron fraction. Look at this prediction here to just get an idea of the type of general prediction you get in cosmic ray models. So a rising positron fraction implies some form of an excess over standard cosmic ray models. Of course, this comes with a caveat. And the first caveat is that you might reaccelerate secondary particles. You might have some sort of non-standard cosmic ray scenario. Or, more naturally, you have something that injects positrons. For example, dark matter. Or, unfortunately, something a lot more prosaic, like young pulsars. Myself and others have shown repeatedly that pulsars can be responsible for the observed positron fraction in a very natural way, and without invoking any extra parameter. For example, in this fit, there's no parameter that I'm playing with, in the sense that the shape of these two predictions that correspond to two nearby pulsars are fixed by the observed age of the pulsar and with the fact that we think positrons in a magnetosphere are accelerated by Fermi second order acceleration type mechanisms. And these predictions that I made with my then graduate student Tim Linden are perfectly fine with the new 2015 data that AMS released. Notice that the AMS collaboration sometimes makes a big deal that there is a cutoff that the positron fraction seems to have. Well, that's not at all a smoking gun for dark matter. In fact, it's very simple to convince yourself that that's a completely general prediction of pulsars. Take the energy loss equation for cosmic ray electrons that lose energy quadratically with energy through inverse Compton and synchrotron. You integrate this over the age of a pulsar. So you have a pulsar that started injecting electrons at some point. Well, you end up with a cutoff. There is a maximal energy that depends inversely on the pulsar age. So as the pulsar gets older and older, the positron you observe at the Earth have lower and lower energy, as it should be. But it's a sharp cutoff. It's an absolute cutoff that just informs us of which system has injected those electrons and positrons. So known pulsars are okay. In addition, explaining positron access with dark matter is problematic. It's problematic on a number of levels. It's hard to come up with models that are not ruled out by orthogonal interpretations, and it's hard to come up with models that produce the right spectrum. But of course, for theorists, problems are opportunities. There's a general theorem, due to an astronomer, that says that any competent theoretician can fit any given theory to any given set of facts. We saw this over and over again with this positron fraction story. So to me, the really interesting question is, can we tell pulsars apart from dark matter? Can we differentiate directly between these two scenarios? And if you think about it, one thing you could use is the arrival direction information of positrons and electrons, which is a piece of information we do have. So think about looking in the sky and looking for a dipolar anisotropy, a preferential arrival direction for your excess positrons. If, in fact, the culprit is pulsars, you would expect an excess in the direction of some of the nearby and brightest pulsars. Vice versa, if it's dark matter, you have a very diffuse signal that probably doesn't have any directional information to it. No dipolar anisotropy has been detected so far, but this is so far compatible with the pulsar interpretation. A couple of years ago, I put out a general theoretical argument that showed that if an anisotropy is ever detected, and if you don't have really complicated magnetic field configurations, then you rule out the dark matter. So detecting an anisotropy would kill the dark matter. Unfortunately, we have not detected an anisotropy yet. However, in that study, I was slightly naive because I neglected the fact that to hit a telescope near Earth, these guys have to travel through the heliosphere. And the heliosphere might look small compared to the size of the galaxy, but in fact it's not small compared to the Larmor radius of 100 GeV electron or positron. And so in fact with the student we are using detailed magnetohydrodynamic simulations of the heliosphere magnetic fields to predict how much cosmic ray electrons and positrons in the interesting energy range get bent as they travel inside the heliosphere all the way to us. And the answer is quite depressing. The answer is that the average bending angle for these electrons and positrons is large. In other words, you lose entirely, according to our preliminary results, any direction information at the solar system level, which is very sad. So, while direction information might not be a conclusive probe, there are general arguments against the dark matter origin that, in fact, in my opinion, date back to the 14th century when this guy said that ensia non sunt multiplicanda praeter necessitatem, which means you should not multiply entities beyond necessity. This is William of Ockham. So if you've got something, pulsars, that do explain in a natural way your excess, then you should not postulate that it is dark matter. In fact, here I show you a rare picture of William of Ockham perplexed by 21st century particle theorists working on dark matter. A few months ago, Wired, an online journal, asked me what I thought about the AMS 2015 data, and here's what I said. I said, quote, there is absolutely no reason to think that AMS results have anything to do with dark matter and new physics. And I know it's depressing, and even this piece of paper cannot stand it, but that's where things are for the positron fraction. So let me move now to the 3.5 keV line. This has been very exciting, very interesting. Hundreds of papers have been written on this. So let me summarize what this is about. Back in 2014, a group at Harvard found an excess line compared to standard expectations for elemental lines in that energy range from stacked clusters observed by XMM and also by Chandra, and a particularly bright 3.5 keV line from the Perseus cluster. An independent group in Switzerland also detected this line from Perseus and claimed the detection from Andromeda, from M31. In 2014 also, with my collaborator Tesla Geltman at UC Santa Cruz, we got pretty excited and we wanted to jump on a boat, and we decided to observe the center of the galaxy, and believe it or not, we found a 3.5 keV line there as well. So X-ray lines are very interesting. We've heard of neutrinos. They're very interesting because if neutrinos are the dark matter, well, a special variety of neutrinos, sterile neutrinos, then you expect an X-ray line, very naturally. So what are sterile neutrinos? These are gauge singlets, so they are things that do not talk at first order with the standard model of particle physics, but they do have a small mass mixing term with active neutrinos, so they do talk a little bit with active neutrinos. They are warm dark matter candidates, so they're interesting for structure formation, for example, and they might be connected with baryogenesis through a mechanism known as leptogenesis. But of interest to us is the fact that through this mixing with active neutrinos, sterile neutrinos can decay into an active neutrino and a photon. But since this is a two-body decay, and since sterile neutrinos are much heavier than ordinary neutrinos, these photons have one precise value of the energy, which is half the mass of the sterile neutrino. So if you've got a 7 keV sterile neutrino, you predict a 3.5 keV line. And interestingly, that energy range, 7 keV for the mass of sterile neutrinos, is kind of magic because it explains very naturally how sterile neutrinos got produced in the early universe, and it has many other nice properties that make a 7 keV particle a very natural dark matter candidate. Now, of course, life is never simple. Life is never simple. Now, let's do a little quantum mechanics exercise. So if you have an hydrogen-like atom with a nucleus of charge Z, you know that the energy of the first excited level scales like 13.6 eV times Z squared. And I leave it as an exercise to show that it actually goes with Z squared. Got to think a little bit. So if you have a Z of about 16, your first excited level will have an energy of right about 3.5 keV. However, if you have two electrons, so if you have an helium-like atom, then this number gets a little bit smaller. So it turns out that at 3.5 keV, you have potassium, Z of 19, producing a nice line. So that's a problem. It's a problem. And by the way, in this working on this topic, I learned a lot of things. For example, that atomic physicists are completely crazy. So they use the expression potassium 18 to indicate a doubly ionized potassium ion. And the 18 comes from the fact the potassium ion with 18 minus 1 electrons missing. So potassium has 19, you take one out, and then the 18 indicates one less than that. So yeah, they're head cases. Anyways, so the real question is, can we tell potassium from sterile neutrinos? Both produce a line. What can you do about it? Well, what you could do is use other lines that you do detect in X-rays. In X-rays, you see these potentially bright lines when you observe clusters from the ISM, well, the intracluster medium. And so you could use other elements and some information about the relative elemental abundance to predict how bright the potassium should be. But this is not an easy exercise. Sounds easy, but it comes with two critical complications. Number one, we don't know the temperature of the plasma that inhabits clusters. And the ratio of these emission lines, which are nothing but, these ions get to an excited level and then they drop back and they emit an X-ray photon. So we don't know the plasma temperature. And number two, we don't know the relative abundance of, say, silicon to potassium or argon to potassium and so on. So back in 2014, the Harvard group claimed that it could not be potassium, this 3.5 keV line, because you would need a factor of 20 extra potassium than you expect. Okay, so you just don't have enough potassium for that line to be bright enough to be the 3.5 keV, therefore it's dark matter. This, however, is problematic. And we think that they made two key mistakes. Number one, they used the wrong plasma temperature. And number two, they used the wrong relative elemental abundance. And I will explain to you guys why I think that these two mistakes happened, both of them at the same time. So the first thing is that Bulbul et al. Used a very large plasma temperature. And it so turns out that if you pick a large plasma temperature, you suppress the brightness of the potassium line. But how can you tell the plasma temperature of a cluster? Well, obviously you cannot use different elements because you don't know precisely the relative elemental abundance, but you can use the same element. Okay, for example, two ionized states of calcium, calcium 20 to calcium 19, and use the fact that the ratio of the line brightness for those two lines is a steeply increasing function of temperature. So this is the theoretical prediction for that ratio. This is the observed ratio of the lines. And so the temperature should be here. Okay, this is for a full sample that they use to determine the 3.5 keV line. So something about 3.5 keV or so. However, what they used for that sample was a much, much larger set of temperatures. They postulated that, correctly, that you have a multi-temperature model, but all of their temperatures are much, much larger. And so, for example, if you use T1 here, you get a prediction for potassium that is a factor 4 lower than this point here. If you use their higher temperature, which is above 10 keV, which sounds pretty crazy for a cluster, you get a suppression of a factor 13. So their error, when it comes to temperature estimates, range between a factor of 4 and 13. But there's more. They also claimed that the potassium underabundance was based on solar elemental abundances. But of course, there's no reason why the sun should provide a proxy for the abundance of elements in complex environments such as clusters. However, things are even more complicated because they used the so-called photospheric abundance of potassium. And there exist observations that inform us of how much potassium is inside the sun, the coronal abundances, as opposed to the surface. How do you do that? Well, you wait for things like this to happen. You wait for huge solar flares, and then you take a nice X-ray picture, and you use that. So if you do that, you realize that, in fact, the true solar potassium abundance is a factor 10 larger than what they've used. So what we did was we took into account these complex factors to estimate the potassium brightness of the 3.5 keV line, and we showed that, yes, for clusters and for the Milky Way, there is no reason to postulate that the 3.5 keV line doesn't come from potassium. So are there any other tests that we can use? Well, yes, there are. So number one, you can look elsewhere. You can look in places where there's no potassium, for example. That'd be great. Or you can use data in a different way than using the spectrum. And I'll show you that we did both things. And in both cases, it kind of looks depressing. So actually, before us, a group in Europe observed a bunch of dwarf galaxies where the plasma temperatures are very low, very, very low, and there's basically no, there's basically no elements around, or very, very little. And they observed no signal at all. at 3.5 keV from a collection of archival observations of nearby dwarf galaxies. Also, people looked at galaxies, so slightly larger plasma temperatures, but much suppressed potassium abundance. And again, they didn't see anything at 3.5 keV. Also, we showed that there's no signal from M31, and that was a spurious detection. Finally, and very recently, XMM decided to give a lot of time to the observation of Draco, one of the nearby satellite dwarf spheroidal galaxies, where a lot of time means really a lot of time. It's 1.4 megaseconds. That's huge. That's like, you know, we're going to take the telescope and mostly observe Draco for the next couple of months. So they did that, and for such large observations, the data becomes public immediately. So even if it was a competing group that got awarded that 1.4 megasecond observation, we jumped on the data, we analyzed it, and here are the results. So these are different predictions based on different models for the Draco dark matter density for the brightness of a line that should exist in this 1.4 megasecond long observation of Draco with XMM. And there's no line at all. And these are the exclusion regions at 90% and 99% confidence level. So at greater than 99% confidence level, we were able to rule out a decay in dark matter hypothesis for the 3.5 keV line. This was an interesting exercise because we actually had a very careful referee that got back to us saying that he or she had decided to download the data and examine the spectrum myself. And I largely agree with your conclusions regarding the absence of a notable feature at 3.5 keV and our limits. It's the first time that the referee actually says, okay, this is interesting enough that I'm going to sit down and redo the analysis. So it got confirmed by the referee as well. You can also use data in different ways. What does that mean? It means that if you don't use the energy, you use directional information, the morphology. Where do the 3.5 keV photons come from? And here are the results. Look at the Milky Way. That's how the 3.5 keV line looks like. It looks like pretty much the Fermi bubbles. It looks like a completely non-spherical emission. If you look at Perseus, it does look spherical, but it looks exactly the same as all other brighter elemental lines, and much smaller, much more concentrated than the radius of the typical radius, or the scale radius of the dark matter halo profile for Perseus. What you're seeing here is the cool core of Perseus that is very bright in ICM emission at X-rays. So we convinced ourselves that, in fact, a dark matter decay was not an option for Milky Way data based exclusively on morphology. It was interesting, though, that people had postulated other dark matter models, for example, axion-like particles that get converted in magnetic fields in galaxy clusters into 3.5 keV photons. That's, you know, kind of one more epicycle to the theory, but that is perfectly compatible with our morphological data. Also, since dwarf galaxies basically have no magnetic fields and they're very small, you don't expect any signal from dwarfs either. So this axion-like particle conversion is a viable possibility, but dark matter decay is essentially ruled out at the moment. So strong stellar neutrinos are very, very disfavored from X-ray observations. And so what are we looking for in the future? Well, the final word really will come from better instruments, from better X-ray instruments. Specifically, AstroH will be able to tell not only where exactly the line is, because it has exquisite energy resolution, but the energy resolution is going to be so good that you can tell apart from the broadening of the line whether that line comes from dark matter that is velocity broadened or from an element in the ICM that is thermally broadened. And so just from the dispersion in the line, from the width of the line, we will be able to tell conclusively whether it's dark matter or not. But it's not. Very good. And this cues me into the last topic of the day, the gamma ray axis in the galactic center, which is the darkest signal of all. If you look at the number of papers written on these different topics and the fraction of papers written on a dark matter interpretation, you got 78% papers on the positron axis, 85%. We are this little red line here. But I'm actually working on a cool model that will explain the 3.5 keV in terms of dark matter, so I'll be also in the blue. And finally, the gamma ray axis is 95% dark matter interpretation dominated. So what is this? Well, this is the detection of an excess of gamma rays from the very center of the galaxy. This is a beautiful picture of the gamma ray sky taken with many years of Fermi data. And if you think you have a good enough model for the diffuse galactic background, you can subtract it off and see what's left. So that's what these people have done over and over again and over, using the same background models and over, very surprisingly obtaining the same axis. And everybody got very excited. Scientific American got very excited. The New Scientist got very excited. But then The Economist got very excited. And I started to become nervous because I knew that The Economist has a tendency to get things right. In fact, when they made this prediction when I was a little kid, and they were right. So, what produces the galactic center axis? What is the culprit? Well, to me, this is very interesting because if you think about vanilla dark matter, if you think about, come up with a dark matter model, come tell me how it looks like, well, it should produce a gamma ray axis just like that. The morphology is squarely what you predict for an NFW square type profile. The spectrum is exactly, give me your vanilla WIMP, that's what you should see. And there are constraints from dwarf galaxies, stuff that I work with Alma here, from radio observations, from CMB, but they're all sort of okay. So you are sort of unable to conclusively rule out that that's dark matter using other frequencies or other objects. But even more concerning to me is the fact that the most obvious astrophysical counterpart, which is a bunch of unresolved pulsars, has very good reasons to be the wrong explanation. For example, the morphology is really not okay. Okay, pulsars are, they're born in the galaxy, they're born in the disk. And so there's no reason why they should look symmetric like the axis looks like. The spectrum is pretty much not okay because we do observe pulsars in gamma rays and the gamma ray axis from the galactic center does not look like that. And finally, there doesn't seem to be enough. You can use methods, for example, X-ray binary observations to count the number of gamma ray pulsars there should be there that you can't quite resolve, and you fall short of explaining the brightness of the gamma ray axis. So it's kind of, exciting. So what produces the galactic center axis? Well, I think that that's a wrong question to ask. That's a wrong question to ask. Rather, the question that we should ask is the axis there? Is there an axis at all? And of course, the culprit, as always in experimental physics, is do we have a good enough background model? I'm a particle physicist, and I know exactly what a good background model is. You've got your collider, you've got your standard model of particle physics, you sit down, make calculations, and then you test it with your machine. You have an experiment that allows you to verify whether or not your background model is good. Here things are more complicated because we can't quite turn on and off cosmic rays in the galaxy and make sure that our diffuse background works. So let's understand a little bit better what this diffuse galactic emission is about. Well, the bulk of the interesting diffuse galactic emission in gamma rays at those energies comes from processes that look like this. You've got supernova that accelerate cosmic ray protons, and these guys travel in the galaxy. There's some transport that describes the way in which they travel in the galaxy, and then at some point they hit interstellar hydrogen, which is just a bunch of protons, and they produce what proton-proton collisions produce, pions. Okay? Charged pions and neutral pions. Neutral pions produce gamma rays because they always decay to two photons. So what we care about is where the gas is, where the cosmic rays are, how the cosmic rays travel in the galaxy. Interestingly, every group that has ever analyzed the galactic center axis has always assumed the following. They have assumed a two-dimensional model for the gas density distribution, a two-dimensional model for how cosmic rays travel in the galaxy. They've assumed that the problem is time-independent, that you can go to a steady-state solution. Well, we know from kindergarten that it's much easier to solve the steady-state solution to a partial differential equation than the full-glory time-dependent solution. So there are good reasons to make these assumptions. It's easier. And finally, they've used very simple models for where cosmic rays are injected. So what my group has set out to do, and has done over the last few years, is to challenge every one of these assumptions, to see whether if you change one of these points, you get an effect that is close or not to the observed axis in the galactic center. So what we want to do, what we're working on, is the next generation of diffuse gamma ray models, which means going 3D, in where the gas density looks like in the galaxy, going 3D in the cosmic ray transport, in diffusing cosmic rays in a way that accounts for the fact that the galaxy actually doesn't have azimuthal symmetry at all. And number three, there are time-dependent effects. Right? We see the Fermi bubbles, for example. We see supernovae going off. We see many things that inject at some point in time, and that point in time might be pretty small. Okay, so it might matter. Transients might matter. And finally, and to me most excitingly, we've thought hard and long about where cosmic rays should be injected in the Milky Way. So let me show you a little bit of these results, but I'm going to focus especially on number 4. So the 3D gas density distribution of the galaxy looks like this, right? So we are here, and this shows clearly that this is a map of the galaxy seen from above, of where molecular hydrogen is. And you can see that it's not at all azimuthally symmetric. In fact, you can see these very high densities, for our special luck, exactly aligned along the line of sight of the galactic center. So that's very bad. It's very bad, because it means that you have a lot of cosmic rays that interact with this very dense gas density along the line of sight, and you can tell where a gamma ray comes from. So it's an important effect. In fact, it's an effect that has the same order of magnitude, going 3D in the gas density distribution, as the excess itself. What about 3D cosmic ray propagation? Well, this is a more subtle effect, but of course you need to take that into account if you want to account for 3D gas density distributions. And the effect seen here is on the order of a few percent. But again, it's large, maybe as close as 5% in the center of the galaxy. What about steady state? What about a burst of cosmic rays? Well, we showed with my graduate student Eric Carlson that suppose you have the freedom to decide when to inject cosmic rays in the galactic center. If you do, then you can easily reproduce the galactic center axis. And we don't think that that special coincidence really happened. But what our study showed is that, hey, transients matter very much. Because if you imagine a transient that is 1 million years old in the galactic center, wait a second, maybe the Fermi bubbles, yes, then the galactic center axis is essentially explained. This is a fit from our data to the galactic center axis. But what I'm really excited about is what we found recently about cosmic ray density source distribution. So where should cosmic rays be? Well, in the past, people have used cosmic ray source distributions that look like this, like a donut. There's nothing in the center. And I'm serious. Every group that has ever worked on the galactic center axis has assumed that there's no injection of cosmic rays in the center of the galaxy. Now, this cannot be true. This is certainly wrong, because we see star formation in the galactic center. There are supernova there. There must be cosmic ray acceleration in the center of the galaxy. So why is everybody forgetting about it? Well, because, for example, they use as proxies to where cosmic ray sources are the observed distribution of pulsars or of supernova remnants. But there is a huge selection effect when you look towards the galactic center. You don't see them because they're obscured. They're hard to point out. And so these samples of pulsars and supernova remnants go to zero in the galactic center because there's no observed pulsars or supernova remnants there. But it's totally artificial. It's not at all physical. So what should you use? Well, what we said is we should use something that is a proxy to star formation. Okay, you got supernovae if you form stars. Okay, you got supernovae if you form stars. Not only. This is a first approximation. So what we do is say, take molecular hydrogen and give me a prescription to connect that to star formation, and observers have done that, Kennicutt-Schmidt law, for example. And we're going to use that for a fraction of all the cosmic rays injected in a galaxy. Why a fraction? Well, because cosmic rays do diffuse. Okay, so it's true that part of them are young cosmic rays that should be close to star-forming regions, but the rest, are all over the place. So we did that, and we looked at what the cosmic ray density distribution, source surface density looks like. And again, these are models that people have used as a function of the galactocentric distance. You see that they all go to zero. Some of them, based on OB stars, they go to zero all the way out to 2 kiloparsec. No cosmic ray sources all the way out to 2 kiloparsec. It's completely crazy. Our model, if you postulate that 25% of cosmic rays are in what we call star-forming regions, whatever proxy we use for that, you see that correctly you put some cosmic rays in the center of the galaxy. Well, that's okay. That's good that we tried this, but how does it look? We know what the diffuse galactic gamma ray emission looks like very well. We have a very detailed picture. So if you start messing up with your diffuse model, I don't care that you do well here. I want to know how you do throughout the entire galaxy, okay? Because, of course, the galactic plane extends much beyond the galactic center. And interestingly enough, what we found was that the best fit to the galaxy overall in the galactic gamma ray emission comes if you do postulate that 20 to 25% of cosmic rays originate from star-forming regions, or quote, star-forming regions. So we get a better fit than the models that people have employed before by just postulating this physically motivated location for the injection of cosmic rays. So that's great, but what about the galactic center? And here's what happens. This is the spectrum of the galactic center axis if no cosmic rays trace star formation. Then you crank up the fraction, you go up, and as you get to 20 to 25%, the axis has decreased by almost an order of magnitude. So it really fades away. Not only does it fade away, it changes its morphology in a way that no longer looks like dark matter at all. So for example, here I plot the angular dependence of the axis. This is what you predict for Navarro-Franken-White profiles. And you see that as you crank up the fraction, you get to a galactic center axis that is very, very weak in the center of the galaxy, and that does not look at all like what you would expect for dark matter. So I think we are really making important progress towards understanding galactic gamma rays, and progress that is relevant to the question of the galactic center axis. In particular, I think that cosmic ray injection sources and 3D models are very, very important. But my take is that I don't think we're ever going to get good enough in our understanding of the background as to extract a dark matter, new physics signal from the diffuse gamma ray observations of the galaxy. So is dark matter detection with gamma rays possible at all? And the answer is yes. In fact, we have a paper where we show that if you were to observe a monochromatic gamma ray line, that's not enough, that is diffuse, so if you observe a diffuse monochromatic gamma ray line, then there's no astrophysics counterpart that could possibly explain that. That's pretty cool. It's pretty cool because that line has been observed at 130 GeV. Unfortunately, That line was a statistical fluke. It was discovered in 2012 by Christoph Weniger, and then Weniger himself showed that it was just a fluctuation. So it went away. There's no 130 GeV line. So, positron excess could be dark matter. William of Ockham tells us that very likely it's not. It's pulsars. 3.5 keV line. Dark matter decay is essentially ruled out, but there might be other new physics explanations, one of them axion-like particle conversion. And finally, the galactic center gamma ray axis, also very, very hard to pass the burden of proof. So what else? Well, there's a lot of else. Okay? The 13 TeV LHC is going to be great. You've all heard about the 750 GeV diphoton axis. Well, folks, if that holds up, that's going to be a game changer. That's going to be a game changer at many different levels, possibly including dark matter. So we'll see. We'll see what happens there. Radio surveys. There's a lot of action going on at radio frequencies that will impact our understanding of dark matter in the early universe, in the late universe, and so stay tuned there. Astro-H, again, will settle once and for all the nature of the 3.5 keV line, but it will also open a window for more detailed studies of motivated dark matter candidates. Opening up the high-energy gamma ray frontier with the Cherenkov telescope array will be very, very exciting, and so I look forward to that as well. And finally, direct detection is now in full swing with Generation 2 experiments, which, coming from a theorist, is really exciting because they're going to test some of the theories that I spent many years on, and I think they're very, very well motivated. So there's a lot of exciting things down the pipeline. And let me close here with a picture I really like. I don't know if you can make it out. This is a painting in front of the actual scenery there. It's a picture by a painter called René Magritte that says, everything we see hides another thing, and we always want to see what is hidden by what we see. And I thank you very much for your attention.
We have time for questions. The first one.
So in the same spirit of looking for the simplest models, don't you think that the simplest model for dark matter will be that where dark matter only interacts gravitationally?
Well, that's not necessarily the simplest, because you got to define what you think is minimal. What is minimal? So I can tell you that minimal means that I have the least degrees of freedom in the quantum field theory sense. And so you can add a real scalar field. And so that comes with a certain number of new degrees of freedom. Or maybe you think about parameters, and then you want a minimal dark matter model that is minimal in the sense that it contains the smallest possible number of new parameters. So and in both examples I gave you, you would have extra interactions with the standard model in a very natural way. In the real singlet, you would have naturally renormalizable operators that would connect it, or portals that would connect it to the standard model, so you would have interactions. And in the case of minimal dark matter, the minimal thing you can do is to add a particle that is charged under SU2, and you have only one parameter that is free, the mass of this new object. So there are numerous arguments by which, in fact, the most minimal dark matter model has extra interactions besides gravity. So it is not necessary, but that doesn't mean that a really minimal dark matter candidate should only have gravitational interactions. Catherine, I think, had a question. Oh, go ahead.
So the story of the 3.5 keV is very interesting because you spoke about clusters. Indeed, the intra-clusters medium is preferentially enriched by massive galaxies whose element abundance ratio are indeed non-solar. Okay, so there are other lines that can give you the temperature pretty precisely, and these are cool core clusters. Then there are other class of clusters where dwarf galaxies like the dwarf spheroidal you have used may play a role. Now the thing with dwarf spheroidal, they are subsolar in element abundance ratio and also very metal poor. Yeah. So you would naturally expect a variation of the potassium, even if this is a marginal element for chemical evolution, just because of metallicity.
Yeah.
I'm not sure I understood your conclusion. So the fact that this line was barely detectable in the dwarf spheroidal, how do you...
Was not detected at all.
Okay, but we know the dwarf spheroidal are full of dark matter from the mass to light ratio.
Exactly.
Yes. So the conclusion
Is that
because the metallicity
it, is that it
changes.
comes from potassium. You
So it is
observe
a metallicity effect.
It is a metallicity effect or a relative elemental abundance effect.
Okay. Mostly because we know the dwarf spheroidal are full of dark matter. I would take it this way because it is also underabundant. So if you don't find it, it's not a metallicity.
Yeah. Yeah.
So that's the thing.
So it goes very well with the notion that this 3.5 keV line comes from potassium that has an abundance in clusters, like you said, that is not at all solar. There's no reason for it to be solar.
Suppose we are lucky and the LHC result really holds and there is something at 750 GeV. What is the dark matter community going to do to connect it to dark matter, right? Because it might be just a random new particle. So what would be the strategy?
Yeah, so what you certainly know is that the dark matter has nothing to do with whatever 750 GeV particle it is, because that particle decays into 2 photons. That's how we see it. But that particle could very well be the portal. In other words, the particle that connects the dark matter to our visible sector. And so folks have thought about it and have come up with simplified models where you've got a dark matter candidate that is connected through this 750 GeV portal to the visible sector. And you can sit down and pick minimal models or less than minimal models and make predictions for what you should see at different dark matter experiments. Now, I think at the moment is very, very speculative to draw any conclusion on the dark matter sector from what we're seeing at the LHC, but there are prospects. And one of the things that we do see for the 750 GeV line is that this 750 GeV particle, if it's there, it couples with protons. And so you can make, if that's the same particle that couples to the dark matter, then you can say, well, you've got to have at least some degree of direct detection rates. You've got to have at least some degree of, production of strongly interacting particles in dark matter annihilation events. So you can make statements. But for example, it's going to be very hard to pinpoint the dark matter mass from LHC data if the 750 GeV particle is the portal. But it's exciting nonetheless.
Any other questions?
Yeah.
I mean, there is no star formation in the bulge.
Yeah.
If you go close to the galactic center, there were evidence of anomalous sort of cluster. The group of Rainer Genzel have seen that, in which you see clumps of stars, but they don't come up in a stellar population mode in the sense that you have just stochastic stars that do not make up for a stellar generation. In other terms, people have excluded star formation. On the other hand, you could exploit supernovae type 1 to give you that access. You don't need to go through supernovae 2. That was my point.
Yeah.
Would you get, because this would be more consistent with other things we know about the center of our galaxy.
Well, so there's a couple of things that you got to keep in mind. One is that we are interested in pretty extended periods of time, million years time scales. So you've got one snapshot of the galactic center now, but what happened between what you see now and 1 million years ago is an extrapolation that that has some uncertainty to it. But I think more importantly, you should ask the question, okay, is it reasonable or not to think that the galactic center does not accelerate cosmic rays? And star formation is one thing that if there's a lot of molecular hydrogen, you genetically predict. But you can also think about such a star. That thing probably did accelerate cosmic rays because we see the Fermi bubbles. And so there's a lot of action in the galactic center. It's a very dense region, complex, and like I said, over 1 million year timescales, I don't think it's reasonable to assume that there's no cosmic rays injected within a few kiloparsec of the galactic center.
We have time for one last question.
So concerning the 3.5 kilo-electron volt line, you say something about action possibilities. Do you mean the action-like particles or the true action that solves the CP problem that can explain this 3.5?
So these axion-like particles are not QCD axions. They're not QCD axions. They're axions that are not even the dark matter, in fact. So you've got some particle that decays in a way that it produces an axion-like particle that has whatever teeny mass it has, but an energy of 3.5 keV. And then this guy, through a standard Primakov type effect, gets converted into a 3.5 keV photon. Now, I got to tell you about what we're working on because I'm really excited about it. So you can think that the dark matter has an inelastic dipolar interaction. In other words, a vertex that connects a photon to two different dark matter particles at different masses. And so if the mass difference is 3.5 keV, you can have excitation of the true dark matter particle into the other one that then decays back to the lighter dark matter particle, producing a 3.5 keV line. And in fact, these excitations are triggered by the thermal plasma. Because at 3.5 keV, you have enough steam for protons in the ICM or in the ISM to kick dark matter particles to the excited state that then decays down. So in our model, in fact, this is completely general. You predict X-ray lines out of thermal excitation of exciting dark matter. So you can come up with crazy models. And our model works perfectly fine in explaining the fact that you don't see this thing in dwarfs because you don't have gas. You see it weakly in the galaxy, and you see it in clusters. Yeah. Any competent theorist can fit any given set of data.
Okay, we thank Stefano for his lecture. Thank you.